People enter a line for an escalator at a rate modeled by the function r given by r of t, where r of t is measured in people per second and t is measured in seconds. As people get on the escalator, they exit the line at a constant rate of 0.7 people per second. There are 20 people in line at time t equals 0. Alright, so we're going to start with part A, which says how many people enter the line for the escalator during the time interval of 0 to 300 seconds. Okay, so we're looking for people entering the line, which really means we're going to have to use only our rate in and not have to worry about our rate out just yet. So I know that my rate in is equal to r of t, and that my units for my rate in are going to be people per second. And that's my rate in. Now, if I'm trying to find my total people entering the line, I want to get my units to be just people. I don't need my seconds there. I don't need it to be with respect to time. So what I'm going to do is I'm going to go ahead and take the integral of my rate in from 0 to 300. So let's go ahead and do that. So we'll say integral from 0 to 300 of r of t dt. And we can do that right on the calculator, and we're going to get just about 270 people. Notice this is no longer as it relates to time. So that's going to be our answer for part A. Moving right along to B. During the time interval 0 to 300 seconds, there are always people in line for the escalator. How many people are in line at time t equals 300? So we're looking for total number of people in line, which means we're going to have to use both our rate in and our rate out. Okay, so I'm going to call this our population at a given time, and that's going to be measured in just people. Our population at a given time is going to be equal to, well, the integral of our rate in. So same thing we did before. And this is still from 0 to 300, so I can go ahead and leave that the same. But that just tells me how many new people joined the line between 0 and 300. I also know that at time t equals 0, there were 20 people already in line. So I'm going to add 20 to that. So this first part right here tells me people who joined the line within our specific time constraints of 0 to 300. But that doesn't give me the population. I need to subtract the people that left the line. So I'm going to say minus our rate out of 0.7 people per second. And I'm going to multiply that, because I just want people, I'm going to multiply that by our time of 300 seconds. That'll tell me how many people left the line after 300 seconds. Okay, so let's evaluate that. We already know the definite integral from 0 to 300 of r of t dt. We already know that's 270. Then I'm going to add my 20. Oops, forgot my equal sign. And then I'm going to subtract 0.7 times 300, which gets me 80 people. Alright, on to part C, which says, for time is greater than 300 seconds, what is the first time t that there are no people in line for the escalator? So again, we're dealing with people rather than people per second. So I know that after or at 300 seconds, there were 290 total people that had joined the line, right? Because we had 270 people that joined, 20 people already in it, so we have 290 that have kind of flowed in. So then I just need to go ahead and subtract from my number of people coming in. I need to subtract the number of people going out, which is going to be our rate out of 0.7, but we don't know our time. That's what we're trying to figure out. And we're going to set this equal to 0. So in other words, we've got up here people in, here we've got people out, and we want to know when the total, when the population is 0. So we're essentially using the same function that we created up in part B. Okay, so doing that out, this is just going to be some algebraic manipulation. We'll add 0.7t to both sides. I get 290 equals 0.7t. Divide both sides by 0.7. And I'm going to get t equals 414. Whoops. There we go. 414.286 seconds. You may have gotten 414.285 if you rounded a little bit differently than me. So that just means at 414.286 seconds, that's going to be the first time there are no people in line. Alright, moving right along to D. For time is greater than 0 and less than 300, at what time t is the number of people in line a minimum? To the nearest whole number, find the number of people in line at this time and justify your answer. Okay, so number of people, that's just going to be our population. So we wrote up here what our population was, actually, and this is our population specifically at 300, t equals 300. But I'm going to just first write my population in terms of t, just so it's a little bit more general. So that's going to be the integral from 0 to my upper bound of r of t dt plus 20. Okay, that's just our number of people coming in given a specific number, a specific time constraint, and then so we'll label that. People who joined, and then I'm going to subtract my rate out times my time, and this is just people who left. Okay, now hopefully we remember that finding the first derivative of a function will give me critical points, and those critical points may be the location of minima and maxima in the original function. So we're going to go ahead and do that, and then I'm going to draw kind of a sketch of the resulting graph. So we're going to say p prime of t, and just with our knowledge of the second fundamental theorem, I know that from 0 to t of rt dt, that's just going to be plain old r of t on its own. 20, that's going to go away, that's a constant, and then I'm going to end up with, over here, minus 0.7. We're going to just get rid of that t. Okay, so now I need to just figure out where this is equal to 0. So this is going to be another calculator part here. So I'm going to just say 0 is equal to r of t minus 0.7. When is that true? Well, that is true at time t equals 33.0133 and 166.575. So t equals 166.575. Now this is what the graph of our first derivative of our population looks like. It's a little something like this. And right here we've got ourselves t equals 33.0133, and right here we've got ourselves t equals 166.575. Now, we're looking specifically for the minimum value. And what we should see here is I have two critical points, but only my first one has a negative slope that changes to a positive slope. That defines what a minimum is. Over here, when t equals 166.575, well, in that case, we have positive going to negative. So that would be a maximum. So we don't have to worry about that. So let's go ahead and put our value of t equals 33.0133 into our original function here. So we'll say integral from 0 to 33.0133 of r of t dt plus 20 minus 0.7 times 33.0133. Okay, and sorry, that is not p of t, but that is p of 33.0133. All right, and that's going to get us a value of 3.8 people, but we need to round to the nearest whole number, which means this is going to be 4 people. Now, you're probably tempted to just stop right there and say, okay, we found a minimum. That must mean that's the lowest number of people. But what we have to do first, let me just adjust my camera. what we have to do first is, because our original function is continuous and over a closed interval, we have to test our endpoints. So my original, let's see. So I need to test my population at 0, and I need to test my population at 300, because those could, in theory, be lower than my minimum I just found. Now we could go through and plug these into our population function that we made here, but we don't really need to do that because we already know what the population is at 0 because it's given to us in the question. We know there are 20 people in line at time t equals 0. So p of 0 equals 20 people. And 20 people is obviously greater than 4 people, so we don't have to worry about that. And our population at 300, well, that is, again, from an earlier section, we know from part B that there are 80 people in line at p of 300, or when t equals 300. And 80 is bigger than 4, so we cross that out. So we say we have a minimum of 4 people at t equals 33.0133. That is going to be by closed interval